We're going to have another look at this idea of locus, whatever it's called. Remember, all we're really talking about with locus, number plane graphs. But now we've got different ways, and we saw some earlier, you remember, with the circles. We had a brief chat about lines and circles, and let's look at it in a little bit more detail. So circles. There's our standard circle, centre at the origin. We saw before, that rhymes. We saw before we could write that as z times z conjugate equals r squared. Because number times its conjugate, sum of two squares. But now we know about modulus, we've got a neater way of writing it. We could just simply say the modulus of z is equal to r. Because remember, modulus, distance from the origin. So if the centre is the origin, then all the points on that circle would have the same modulus. So that's a neater little way of writing the equation in a circle. Modulus of a complex number is equal to r, the pirate letter. Now, if the centre is somewhere else, and what we saw before is we could write it as z minus the centre, so w, times the conjugate minus the conjugate of the centre is equal to r squared. But now we've got a much, much neater way of writing that. Because I can simply say the modulus of z minus w is equal to r. Imagine that radius that I've drawn in is a vector. Because the vector would be head minus tail. Well, on the circumference are all the possible z's. And the centre is w. So head minus tail would always be z minus w. And the radius is the length of the vector. So we can simply write it as the modulus of z minus w, head minus tail, is equal to the radius, and we know the centre, therefore, must be w, because that's where the vector's going to, or coming from. So we're going to express these circles in terms of z. So there's the Cartesian equation. X squared plus y squared is equal to 16. So an easy one to start off with. They would be, spit it out. That would be the same as simply saying, the modulus of z is equal to 4. Because we know that's a circle, centre at the origin, radius 4. So if we were to join z to the origin, so z minus 0, which is just z, the length of that vector would always be 4. If you did put it the other way, you'd write it as, well, z conjugate is 16. Here's one where the centre is not the origin, so we'd have to complete the square to find out where the centre is. So move the constant to the other side, add half the coefficient of x and half the coefficient of y squared, and we end up with x plus 3 squared plus y minus 2 squared is 25. So I know the centre is the point negative 3, 2, which would represent the complex number negative 3 plus 2i. So head minus tail, z's on the circumference, to the centre, so minus 3, so I end up with plus 3, minus 2i. The length of that would be the radius, 5. And if you really wanted to write it in the other form, I don't know, maybe you think it looks pretty or something, you'd write it like that, z plus 3 minus 2i, conjugate of z, and then conjugate of the 3 plus 2i is 25. Find the centre and the radius of this particular one. So now we've got it in that form. Okay, well, what are they telling me? I'm getting z, and I'm joining it up to the point 5, 1. And the length of that is always 2. Right, so I know its centre is 5, 1, and I know the radius is 2. Done. Okay, here's one that's in the other form. But that's okay. We can do it. Let's do it. We know it's in the form z plus a number here, conjugate of z, and there's the conjugate of the other number. So this 4 plus I, well, the negative of that must be the centre. It'll be z minus the centre. So the centre must be minus 4 minus 1, and in this format it's radius squared. So radius must be 7. Must be 7. oh, here's something I don't immediately recognise. So if I don't immediately recognise it, I'll probably go back to substituting in x plus iy for z, and then working out what the Cartesian equation is, and then I've got a better idea of what it is. So let's have a look at this. I can always factorise a 3 outside absolute value sign, or any number for that matter. That doesn't really help me. I thought that might give me a bit of a hint, but no, that hasn't really done a lot for me. So, okay. I've squared both sides, you'll notice, because remember, the modulus of z is the square root of x squared plus y squared. So that's why I've got 9x squared and 9y squared there. And on the other side, x plus 2, because that would be the real part squared. Y minus 1, that would be the imaginary part squared. Expand the whole thing out. Collect like terms. It's starting to look like a circle. Let's divide everything by 8. Almost there. Add half the coefficient of x squared, half the coefficient of y squared. X minus a quarter. There's nothing to say it had to be a whole number. Plus y plus an 8th squared is 45 on 64. So therefore, centre, quarter minus 1/8. Radius, 3 root 5 on 8. 3 root 5 on 8. One in the other form. Well, it's not quite in the other form, but it is playing with conjugates. Again, can't really tell just by looking at it. So z times z conjugate is equal to... Said with such enthusiasm. All right, sum of 2 squares, x squared plus y squared. Z plus z conjugate would be... Right, twice the real part, or 2x. Let's substitute that in. Now we've got something we can try and work out. What is the centre and so on. So let's group things. So it would be x plus 2 all squared plus y squared is 4. There we are. Centre minus 2, 0. Radius 2. Right, lines. We talked before very, very briefly about lines. It was horizontal lines and vertical lines. You remember horizontal line we said could be now labelled the imaginary part of z is always equal to c, or a constant. Vertical would be the real part of z is always equal to a constant. Not all lines, of course, are horizontal or vertical. Some are at an angle. Ooh. There you go. I'm just going to draw something in. You see, all lines can be described as the perpendicular bisector of 2 points. Because if you were to find the perpendicular bisector of 2 points, you will get a line. Okay? So, here we go. What we're saying then is if this line is the perpendicular bisector of these 2 points, W1 and W2, we're saying the distance from W1 to the line will always be the same as the distance from W2. It does not matter where we put the point on the line, the distance would always be the same. Imagine it was down here. And we can prove it very easily from congruent triangles. If it is where my finger is right now, you can see we've got the base there with the dash on both sides. I've got a right angle, or an angle, and of course the common line. So side angle side would prove that's a congruent triangle. So therefore these distances must also be the same. It's a funny way of describing that, but I guess what I'm getting at is I'm more interested in the reverse idea. If you see modulus of z minus a number is equal to modulus of z minus another number, we know, that's going to be a straight line. So here's an example. I know this will be the perpendicular bisector of the point 1, 1, who of course was a racehorse, and minus 2, minus 1. Now, I could use algebra. If I did not recognise that, again, I could go back to algebra. And there's the real part squared plus the imaginary part squared equals on the other side, the real part squared plus the imaginary part squared. Expand out. But it's not a circle. Because the x squareds cancel, the y squareds cancel, and we get the equation of our line. But if you realised it was the perpendicular bisector, you now have an alternative way of doing it. You could find the midpoint, because obviously that would be a point on the line. You could find the slope. Well, that's the slope joining 1, 1 and minus 2, minus 1. Therefore, the slope we want, because it's perpendicular, minus 3 on 2. We have a point there. We have a slope. Point slope formula. And you see we end up with the same answer. So, a couple of ways of approaching that. But I guess the key thing is, if you see modulus of z minus something equals modulus of z minus something, you know that's a straight line. It represents a straight line. Oh, sorry, I was a bit worried you nodded off there. Be careful though, read the question carefully. It might be a lot easier than you originally think. It just says sketch. Nowhere does it say find it. Just got to draw a picture of it. So, okay, here's a picture. Z to 2i, or minus 2i, so that's why I've labelled minus 2 down there, and z minus 4i. So we're saying z is joining up to the points minus 2 and 4. I know it's the perpendicular bisector. Halfway between minus 2 and 4 is? Yes, very good. That's why the 1's there. And it's the perpendicular bisector. There's my answer. I just simply sketched it. Actually, given that it's horizontal, it's not too hard to work out the equation of. Of course, it's y equals 1. Rays. Who remembers what a ray is? You have lines, you have intervals, you have rays. Rays? Oh, say it again. Yeah. So it has a definite starting point, but then keeps on going. Technically, a line keeps on going in both directions, and an interval has a definite starting and finishing point. So a ray. Here's an example of a ray that starts at the origin, and it makes an angle with the x-axis. That could now be described as the argument of z is equal to theta, because every point on that line would have the same argument, because they all make that same angle. Why have I circled the origin? Well, if you're at the starting point, how can you measure the angle? You haven't gone anywhere yet. So what do I measure? Where do I measure it to? So you always circle the starting point to indicate not included, because I can't work out that one. And if it's not at the centre, there we go. Well, now I'm just talking about a vector here, where instead of joining it to the centre, I'm joining it to W. And so the argument of our vector z minus w would be equal to theta. Let's do this. This is regions in the plane. It just looks a little bit different to what we saw in the junior school. We're going to shade in the region where the modulus of z is less than 1, and the argument of z is in between 0 and pi on 4. Modulus of z is less than 1. Well, if it was equal to 1, we would be talking about units. Oh, who said unit circle? Outstandingly described. Didn't need to say centre or radius, encapsulated it in the word unit circle. Very good. Oh, yes. Okay. So there we go. So it's dotted, you'll notice, because it's just less than and not less than or equal to. Okay. Inside or outside? Yes. Another way of thinking about that modulus, distance to the origin. We want all the points, the distance to the origin is less than 1. So we must be inside, because outside they're going to be further away than 1. All right, so we know we're inside. I won't shade it in yet. Argument of z. Well, these are now what we're talking about, rays. And again, it's just z, so it's joined to the origin. There's the argument that would have an angle of pi on 4. And 0, well, that's a horizontal line. There's argument of z is equal to 0. Notice I've circled the starting point. And we're between those two, because we're in between 0 and 4. So we are inside there, that little bit there. Now, technically, I should do one more thing. Anyone know what it is? Well, not necessarily label them, but circle them. Circle them. Remember, whenever you have a dotted line and so, the point of intersection is not included. All right, enough of me waffling on. 4M, 4N. Fake Cambridge. 1F.